And I'll be presenting, like Martin said, I'll be presenting today our, my presentation on film versus paste when it comes to sinter materials. Once we get that settled, there we go. I'll start sharing my presentation and
Yes, it's coming. It's coming.
yep, get into presentation mode. Martin, can you
It's
see the
there.
presentation?
We can see it. Yes, John, please.
Great, thank you. Okay. So I'd like to start my presentation with a general overview of sintering. What is sintering? Sintering is a method where we can create objects from powders. So essentially what we're doing with silver sintering is we are precipitating out silver in small silver particles, either on the nano or micro scale, and then encapsulating them as some sort of organic to make sure that they don't self-sinter or diffuse into each other. What that allows for is then you can take that powder and formulate it into a paste, which then you can use to dispense onto a surface and apply to your components. Very similar to the solder paste process. The difference between sinter paste and solder paste is that with a sinter paste, there is a step of sintering, obviously, which goes along, and that you do instead of your reflow profiles that you would use in soldering. So the sintering process requires temperatures usually above 190 C with low applied pressure, usually around 10 megapascals for a certain amount of time, can be, upwards of 5 minutes or so. And what happens during that time when you have all your components and your sinter material at temperature, the organics are removed and the silver particles, they begin to, let's see if I can get there we go. You can see here the silver materials, they start to sinter or diffuse into each other, and then the grain boundaries become larger and larger. So you go from many small silver particles to a uniform um, uniform area with some porosity, not much. Usually we shoot to have a porosity around between 10 and 30% porosity. What that porosity does is at first it seems like, wow, that's a lot of porosity, but that allows for some compliance and helps out with the CTE mismatches between your components. So that what it does is it allows it to be a stress relief between the components that you are sintering together. So how does sinter materials compare to solder materials? The answer is, and I don't want to go into it in too much depth here, but many studies have shown that sinter materials are much more reliable than solder materials in general. What we've found, depending on the type of testing you're doing and your application, you can expect a reliability increase between 10 and 10 per, sorry, 10x, so 10 times reliability up to 30 times reliability is what we've seen in thermal cycling. And here we did a test of a sinter material and a solder material on a typical package attach application. We did a thermal shock test or thermal stress test from 150 C to negative 50 C, 30 minutes dwell time in an air to air application. You can see at 0 cycles, very good CSAM results at 250 cycles. You can see that the sinter material has pulled away from the edges a bit, but is still very much intact, where the solder material had it pretty much hit end of life well before 250 cycles. So you can see here in this test and many other tests that have been published that sinter materials are much more reliable than solder. Another massive benefit you get by using sinter versus solder is your thermal conductivity. A typical thermal conductivity of a silver sinter product is between 200 and 300 watts per meter Kelvin. Most solders are 60 watts per meter Kelvin or less. What does that bring for you? What is what does that benefit? What is the advantage to an end user? Well, the advantage is twofold, or there's two different things you can do. You can either maintain your design the same way it is and get a higher power density out of that chip, which we're trying to show here. Because the conductivity is higher, you can just get more power out of the same application, or you can redesign your application and use less die for the same amount of power. The third advantage you get is the ability for higher junction temperatures. Silver sinter will withstand 175 C just fine for pretty much any amount of time. There really isn't a solder out there on the market that you would want to run at that high of a temperature for that long. So those are your three main differentiators between sinter and solder. The sinter materials come in two different form factors that are available on the market. The first one is what everyone is pretty much used to. It's a silver sinter paste. And when I say everyone is pretty much used to this, it uses the same equipment as a solder paste operation. So the first part is going to be the first operation is going to be your dispensing or your printing, where you're taking the paste and printing it or dispensing it, putting it on the target pad or target area where you want the paste. And then you have a choice with your next operation. You can either use your pick and place machine and place the component on the wet sinter paste and then dry it, or you can dry it first and place it on you can dry it first and then place the component dry. The last operation you're going to have is the sinter operation. So you've got at a minimum 4 steps you have to be concerned about, 4 different pieces of equipment. I mean, obviously you can integrate them, but 4 discrete steps and possibly inspection steps in between to make sure that your dispense operation was okay and that you don't have excess voids, excess marks, or an inappropriate dispense where you're not on plane. One of the biggest drawbacks to the operation is that material yields can be low in a printing process. We've seen in our labs, we're lucky to get about 70% yield. In fact, it's even lower. And then the other feature you have to take into consideration is that paste typically comes in either a jar or cartridge, and it may need to be stored at cold temperatures. So you have to have your cold storage, and you have to be able to manage either the jars or the cartridges. And one of the drawbacks to both is that silver is obviously a very expensive material. You want to be able to use as much as you can, so you have to be able to figure out a way to extract the maximum amount of paste from the container that it comes in. I want to take a closer look into the paste process and explain where there are advantages to especially the printing process, but and the dispensing process as well. First part, there's a lot of flexibility when it comes to bond control. You can just essentially, by designing your printing surface, the surface that you print with, by designing that, you can control your bond line thickness, and you can very much control the geometry which you're printing. So you can see here, it doesn't necessarily have to be a square. You have, in this particular example, there's some rounded corners here, which is a big advantage that you get with paste, that you can place the paste exactly in the same geometry as the component requires. So that's this one. And then this one, you can see a application more geared for large area package attach. The other big advantage you get with paste is you can also do a dispensing process if that's what you want to do. And that's what we're trying to show here with this picture. So other advantages you get from paste. There's many formulations available on the market. You can get a formulation specifically designed for printing or dispensing. You can use it for die attach or package attach or topside attach, which I didn't even put in the presentation. Multiple different substrate chemistries. So you can print onto gold, silver, copper, And I've been made aware of pastes that can do other plating or surface treatments as well. And then, like I've said before, you have the advantage of being able to place wet or dry. And then lastly, and I mentioned this earlier, it's familiar. You can use or reuse your existing solder paste equipment. And here I just put in a picture of some typical formats that you can purchase the Sinter paste in. So going to the next slide, let's talk about silver film production and what the difference is between a silver film and a silver paste. So when you're producing a silver Sinter film, what you're doing, the first step you're doing is you're taking the same powder, the same silver powder that was made into paste with a paste product, and you're mixing it into a paste. This paste, though, is specifically formulated for casting. So the next step is you take that paste, put it into your caster here, and cast it onto a plastic release liner. The release liner is there to just essentially hold the Sinter film until you need it for use. That Sinter film on the release liner is then put into a drying oven where it's very, very well controlled to drive off all of the solvents and everything else that makes a paste. So you're left with only the Sinter film. That ends up being a big advantage to a customer who uses it because we are driving off the organics and the solvents in our factory, so you don't have to drive them off. You don't have to dry them in your process when in your assembly process. So that is that's a big advantage. The paste is then spooled up and then sent to the next operation for use. Typically, that next operation is a bulk film cutting into sheets. So what you'll have is a different, based on the equipment that's being used to assemble, you're going to have different requirements on what you want that sheet size to be. This film can be cut into bespoke sheet sizes, packaged up, and you can see here it's a typical packaging format. This is actually our 97 millimeter by 97 millimeter format, and then it's packed up. The sheets are singulated. There's a protective liner put in between the sheets so there's no scratches, and then they're sent off to the customers to be unpacked and used in what we call the DTF operation. This is die attach sintering. You can see here an example of the operation, and it's a lot less complicated than paste. Essentially, you're doing what we call our die transfer film operation. So that is, you're taking the die, you're transferring the silver Sinter film onto the back of the die, then you're taking that die and placing it on your substrate at elevated temperature, typically about 150 C. Once that's completed, you populate as many substrates as your sinter press can hold, send it into the sinter press. Sintering operation is done, and your package is sintered. Then it can go on to the next operation. You can, if you wanted to, you could also put a silver sinter material on the top side of the die and sinter then both the top side of the die and the die in the same step. That is something that we've tested out in our labs, and it works to great success, and it eliminates a step. It has a potential to eliminate a step in the process, but you can see here there's no drying step that needs to happen with the silver sinter film because that's already done in the manufacture of the film itself. So the silver sinter film is a cast and dried silver sinter paste product. Another benefit is that it can be stored at room temperature and has a 6-month or greater shelf life. We're currently doing these studies to show that it can last longer than 6 months, but right now we know that the film does not change characteristically over 6 months in a typical storage. Room temperature, but it has to be in a nitrogen environment, although in the typical locations where this process would be done, nitrogen is pretty readily available, or nitrogen environment, and it's in an easy and convenient to use sheet form factor. Here we go. So let's take a little closer look at the DTF process itself, just the process of actually getting the silver sinter material onto the back of the die. So the first thing you're going to do is take your die, you're going to heat it up on the bond head. Then you're going to take the bond head and place it into the silver sinter film, at what point the silver sinter film will be separated from the bulk film and just put onto the back of the die. You can see here a much more in-depth look at what's actually happening. You're going to have a rubber backer here. The hardness is variable and it depends on a multitude of variables. And the sharpness of the die, what's happening is the die gets pushed down under pressure, deforms the silver sinter release liner and the film itself, and then it actually just cuts this silver sinter film here. So then what happens is that just what we call tacks to or laminates to the die, and then the die moves off, and then you put it into the hot tacking, which is where you take the die with the Argomax on the back and place it onto the substrate. So that's the process. The next slide I have here is a video of the process. So what we're going to do here is, let me see if I can go back to the normal arrow. How do we get the, all right, this worked the other day and it's not working right now. Now we can start the video. So what you're going to see here is we're picking up the die. There's the hot tack, there's the lamination process and the hot tack process, and we'll show that again. So you can see here, lamination, hot tack of the die, one last time, pick up the die, inspect the die, make sure that everything's okay, and then just repeat the process. So as you can see, very straightforward, very simple, and an elegant way to attach the sinter material to a die. All right. I had mentioned in an earlier slide that I could, we have data that shows that there's no difference in performance over lifetime. So that's what I wanted to show here. So what we did is we've been aging this material and then doing shear tests after aging. And the die we're using is a 2.5 by 2.5 millimeter die with gold metallization. And we sinter it, and what you can see here is there's really no difference in the die shear between the first month and the 5th month of storage. And even after thermal shock, the die shear strength still hold up really, really well. Typically in a non-aged, so no thermal conditioning done to the substrate, we look for a die shear strength of give or take 70 megapascals. And you can see here, even after thermal shock, most of the dies still maintain that target value even after the thermal shock. So the thermal shock parameter that we used on this test was -40 to 175 C, liquid to liquid at 1,000 cycles. So this was a very, very accelerated, very harsh test just to prove that the material still holds up after aging. So what about product applications? Let's talk about the end product and the advantages and disadvantages and the trade-offs between film and paste. So when you're silver sinter paste printing, it's a lot to say, there's multiple different ways you can do it. You can do a screen print, but one of the drawbacks to the screen print is that the surface topology is given by the mesh, and there can be different porosities when you're using the screen printing. You can stencil print, which I showed earlier. The drawbacks to the stencil print are threefold. What you can get is you can get a bleeding area. So you can see here where the during the placement process, or even before the placement process, the paste starts to migrate a little bit from where you want it to the outsides, because it is a paste, it's liquid format, so it'll come out to the outsides. there can be air bubbles left in the printing volume, and this can be really difficult to control, especially as your operation goes on and you're mixing different jars or different syringes of paste together. These type of things can kind of come and go, and they can be really difficult to control. So that's air bubbles, and then that includes scratches and other little imperfections in the surface. And then you can also get overheight on edges where it during the printing process, the material tends to wick up at the tends to start out low and then go high during the printing process. And then I kind of mentioned that here too in the stencil printing process, where you can see that the non-planar printing surface. So what happens is at the leading edge, there's a little less material, and the trailing edge, there's a little more material on the white. So that can be one of the non-desirable formats here. So when you go to a silver sinter film, the unique manufacturing process allows for a very flat surface and a very tight tolerance control of the thickness of the material. So these are concerns with paste that you don't have to worry about with film. That leads you to good bond line control and good volume control. And then you can also accurately place the materials. This gives you different advantages, which I'm going to cover in this slide here. So some of the big advantages are, so we talked about what the drawbacks are using paste, and that's bleed out. Well, if you have bleed out, then all of a sudden you have areas that you can't place other components. And you can see that here easily with film. We call this a fillet or a bleed out. So you don't have this with film. And what you can see here is you can actually achieve tighter packing densities. You know, if you're going to have bleed out, you're going to have a no-go zone around that component that's not really required with the paste, or sorry, the film process. Another big advantage, I mentioned this earlier, bond line control. So the initial film thickness is controlled to +or 5 microns. That gives you a precise bond line control. Typically with the typical film that we offer, the bond line is about 20 microns. The shortened process and the placement is much better, can be much better with film versus paste. I wanted to show you some cross sections that we've done that really shows better than explaining what's going on. So this picture here is a silver sinter film attachment, and you can see a very nice edge here where the film just cut very nicely, didn't bleed over. There's no issues. There's nothing. It's just straight in line with the die. Where with a paste attachment, you can see either bleed out or the overheight or the bunching that we saw in the earlier demonstration. So this is these are just actual cross sections of applications that we've done that show the differences between film die attach and paste die attach. One of the big advantages too is with the lack of excess material here, there is no chance for these extra particles to become detached, where you can see here in a further operation that this material, if you bumped into this material or something happened, you could see this material detaching and then becoming a contaminant somewhere else in your process. Another interesting application we've been seeing a little more is what we call embedded dies. We'd like to believe that film is a very good solution to this application. And the reason is, like I showed before, it's a very accurate placement of film. And if there's a really tight tolerance in an embedded die application, you can see here in this corner where this tolerance could be really short, it would be very difficult to get paste to work well in this spot. So what you would do is you can use your film, sinter it onto the die, and then attach it to your substrate. Another advantage you get to the paste is, you know, I had mentioned that that the paste comes in a thickness, but you can do multiple lamination steps to build up your silver sinter material layer and get a larger bond line if desired, or if it's required. Say, for example, in this application, if your stack up requires a larger bond line and larger silver sinter material area. You can do that by doing multiple laminations. Unfortunately, when it comes to package attach, there's not a silver sinter film option. So when it comes to package attach, sinter paste or solder are really the best options out there, and that just depends on the needs of your application, the amount of stress that's going to be done in validation testing. That's going to really define whether or not you're going to use sinter paste or solder paste. Sinter paste has the same high reliability as sinter film, and the straightforward sintering process is the same. And the variable paste placement thicknesses allow for bond lines designed for the application. So you can control those bond lines really well, and you can control the geometry of that print or dispense really, really well with the paste product. So not all is lost. Like I said, I'm really trying to help you work towards deciding which to use for your application and showing you that there's certain applications, certain areas where paste is going to be recommended or the better option, and there's certain areas where film is going to be the better option. So in conclusion, what was I trying to get across, and what was I trying to help everybody learn today? What are the advantages of film? There's a lot on this slide, but ultimately with film, the advantage is it's lower initial startup cost because there's less equipment to buy and there's going to be less labor involved. It also adds a level of flexibility because of the room temperature stability and long storage life. So that's really well geared towards applications where you don't want to put in a lot of initial investment, or maybe possibly a lower volume application where you're not using lots and lots of material, and you need to use a little less material. Film can have a big advantage there. But on the downside to film, the material tends to be more expensive because there's additional operations done by the supplier. Those operations are clearly in the cost of the product. And the bond line is not as customizable as it would be with paste. The advantages to paste: it's familiar, bond lines are customizable, it's super flexible, like I had said, and it's very, very familiar as far as the processing equipment goes. But the disadvantages are the initial investments are higher, the processing time can be a lot longer, especially with the drying process involved. It's susceptible to high material wastes. I mentioned earlier, we've seen up to 30% yield, or it's just only 70% yield, because so much of the paste can get lost during a print process, for example. They can require low temperature storage and a short use time. And then there's high potential for external contamination. So those are really the things I wanted to try to get across in this presentation. And that is all I had. So my presentation is complete for today.